implementing machine learning and taking us beyond the tutorial. Please, a warm welcome for Kyri Paterson.
Hello. So, as you guessed, my talk here is machine learning, life after the tutorial. I'm happy to be seeing you guys in the last stretch right after the break. I did get to choose my own walk-on music, so you guys know. A little bit about me. My name's Kyri. I'm a machine learning enthusiast, avid storyteller, and I work at Symbility Intersect, the company you might know as the one that's printed on your lanyards. So, we're going to go through a few things today. What do I mean when I'm saying life after the tutorial? Well, there's a lot to know about what the tutorial actually means. So first, I'm going to take you, what do I mean by the tutorial? And what is the problem with it? Why is it so difficult to move on? Then we're going to go into the most important thing, and the thing I'm going to rant about the most today, the magic of data, which is like the bread and butter of machine learning. Then after that, this has a bit of crossover with the tutorial, but what comes after data? How do you actually make a product? It's AndroidTO, so we're going to look into what machine learning looks like in mobile. And then some of my top tips for bringing your product from the garage into the actual company. So starting with the tutorial. So you might remember having done a tutorial before, and you think, OK, this is great. What a tutorial normally takes place, it's a product of being able to learn how to use a particular tool. So normally you use something like PyTorch, TensorFlow, and it'll teach you, OK, I have data. I'm going to use this data. I'm going to import it. And then I'm going to end up with a result. I'm going to train and test a model. But that doesn't teach you all the outside of what makes machine learning difficult and also what makes it successful. So we're going to take a specific example of a tutorial that I'm sure many of you have seen before. It's called MNIST. MNIST stands for, well, I forget. Something National Institute of Standards and Technology. Oh, Modified National Institute of Standards and Technology, thank you, which doesn't mean a lot. But what it's most well known for is the MNIST data set. The MNIST data set consists of a bunch of handwritten digits from 0 to 9. What it does is it tries to classify those digits. So the machine learning problem is to classify those digits. So what happens is we feed our algorithm the number 1, for example. The number 1 says, OK, or the computer says, OK, so it looks like this. This is the dark and light parts that I can understand as a computer. And then we tell it this is the number 1. We do this again and again and again. Actually, for MNIST, 60,000 times with numbers from 0 to 1 until we finally get, OK, I'm going to feed it this number 1 that it hasn't seen before. And I'm not going to tell it it's the number 1. It has to guess that the number is 1. So the machine says, all right, there is a 76% chance that this is the number 1 I'm looking at, and a 24% chance that this is the number 7. 76 is the bigger number, so it says this is the number 1. Going through this kind of tutorial, you'll find great accuracy, or you think anyway, of like 95 or 96%, and you'll say, wow, this seems like a really accurate data set, or a really accurate algorithm, until you find out that the most successful is 99.78%. Something you can do going forward and trying machine learning yourself is if you do a tutorial like this, you can go forward and try to improve your own accuracy with your data set that you already have. Now, the reason I'm going over MNIST specifically right now is this example of a pre-processed, normalized, ready-to-go data set that you can just use out of the box without any extra work. But that's not always the case. And a little note here, that 0.78%, the reason it's not 100 is because the data set actually has mislabeling in it. There are some of the things that are a 2 but labeled as a 1, for example, and that's why I can't achieve 100% accuracy. And that brings us into our main point, the magic of data. So if there's one thing I really want you to take home today, and to remember when you go ahead and think, I want to do a machine learning project on my own, I want you to remember that your algorithm is only as good as your data. It doesn't matter how good your models are. If your data is flawed, your model will not work. That MNIST data set and that not quite 100% is an example of your data being bad, or some of your data being bad. And that's data just being straight up wrong. it's incorrect. And that's the easiest problem you can see in data. I mean, it being wrong, obviously that's a problem. But that's not the most important thing. That's not the hard part. So when I talk about good data, I'm not necessarily talking about just whether the data is actually good or not, whether it's valid. It's whether the data can be understood and compared accurately to a computer. We call this normalizing data. So when I described the MNIST data set before, I described it as pre-processed normalized data. And what that means is it's grayscaled, all the images are reduced to 28 by 28 pixels, and they're all anti-aliased. And as a result, they make them easier to compare. The best example that I thought of in the real world is apples and oranges. Everyone's heard about you can't compare apples and oranges. What if you have a problem where you kind of need to compare apples and oranges? One thing you can do is try to normalize them or make them more similar to each other. In this case, we're going to throw them in a blender, and we get some orange juice and some apple juice. Now, the taste and the color of the liquid are things that you can compare directly. They're more similar, but they're only sort of similar. When you think about it, why is this data good or why is it bad? If we care about the shape of the apple or the texture of the orange skin, this isn't going to work. This normalization is going to fail because we lost some of the key features and the most important things that we need to know from the data set. But if we only care about the taste or the color of the liquid, this is a perfect way to make a comparison. That applies to the MNIST as well. So for example, let's say a bunch of our digits were in multiple colors, and we wanted to find out if the number and the color. So we want to say this is a green number 7. We'd care about the color, and we'd need to include that. Turning it into black and white would remove that important feature that we need. But if we don't care about that. We only care about what the actual label is, what the number is. And as a result, putting it into black and white means there's less features to cloud the data. We take the features we care about and make them important, and we remove or we make less important the features that we don't care about. In data science terms, this often means something called feature scaling. Feature scaling, for example, I'm looking at the housing market. The houses come with, let's say a 3-person house costs $60,000, and a 4-person house costs $100,000, maybe in like Newfoundland or something, definitely not here. But when we take these numbers, well, you might notice that 3 is a lot smaller than 60,000. And when we put those features into a computer, it might end up rating that 60,000 way more than the 3, even though the 3 is still an important piece of data to describe what that house is. And a way we can handle that is called feature scaling. So a common way to do that is to scale features between -1 or 1. In our case, everything's a positive number, so it'll be between 0 and 1. We take our biggest number, 100,000, and we divide everything of that feature set by 100,000. So our house that costs 100,000 is going to be worth 1. Our house that's worth 60,000 is going to be worth 0.6. We do it again with our people. So the number of people in a house, we divide it by 4. The bigger house is going to have a value of 1. And the house with the less people is going to have a value of 0.75. The relative distance between these features and the data is the same, but now they're on the same scale, so you're not at risk of something being more important than something else. This also makes it easier, the math easier for the computer, so you don't end up with hundreds of thousands of zeros in your math. And it just saves space. So make sure you normalize your data when you get into it. Now I'm going to go into a couple anecdotes here. Oh, right, that's also not the only way to normalize. You can also do it by logarithmic scales or all sorts of different ways, but this is just an easy one to explain. So I'm going to go into a couple of anecdotal examples, starting with an interview I had not too long ago with a bright data scientist who told me about a problem she had at a previous job. And the problem was, let's go over her solution first. So she was trying to detect if a document that she had was fraudulent or not fraudulent. This is called a binary classification problem, or yes or no, really. It can be reduced to 2 things. MNIST, for example, is a classification problem with 9 possible classes, 10, because it's the numbers 0 to 10, whereas this one's just 2. Binary classification is interesting because you can just say yes or no. So what was her problem? Well, 3 out of 1,000 cases were fraud, or about 99% of the cases are not fraud. She takes her data, and she trains her model with it. She tests her model and gets the accuracy, and it's 99% accurate. That seems pretty great, right? Well, I'm going to put a question mark there. If you see the number 99% up there twice, that's not a mistake. The thing is this algorithm would always guess that it's not fraud, because it would be right 99% of the time, because that's the cases you gave it, right? Well, that doesn't actually solve our problem. Guessing not fraud every time ended up being accurate, but not really. It didn't solve the problem. So what kind of a problem is this? Well, she ended up using a solution called SMOTE. And there's a lot of ways to equalize your data to make it a little bit more even. You can take your class that has a lot of data and cut it all off, so then there's the same amount of each class. You can try to mimic data into the small class, but this is a really great way that a lot of people tend to do it. There are a bunch of other ways you can look into as well. So this is a way of equalizing data. I'm going to give you a high-level overview. So we have a majority class, where most of our data is. And then we have a minority class, where it only contains a little bit of our data. What SMOTE does is it says, OK, I'm going to compare this set of minority data to a subset of the majority data that's the same size. And I'm going to say, OK, we're going to train it with this. Then we train again. And we cut off the majority class, so we have a smaller amount, or so we have less left, and then we do the comparison again. And then we do it again and again and again until we have sufficient data for our product. And that ends up equalizing the ratio to be closer to 50-50 instead of 3 to 997. And that's a good way to make sure that one of your classes isn't overrepresented. However, unlike this example, SMOTE allows replacement, so the majority class data points can appear multiple times, and it's a little bit more complicated than what I just described. So if you're interested in looking into SMOTE, I'd highly recommend looking it up. So I'm going to go into my second anecdote now. Let's say our data is fine. Everything's equal. Life is good. Well, I'm going to hit you with another binary classification problem that I heard recently from someone I know. And we're going to look at claims this time. So our claims can be approved or denied, yes or no. So here's basically how it works. We say, OK, we're going to figure out like a point score of how important this data is, and whether we're going to approve or deny. So if anything's above like 62% or 62 on our point score, we're going to say it's approved. And if it's not, it's denied. Well, he had a problem. The benchmark changed. And as a result, all this data in between, this approved and denied, isn't right anymore. Is it approved anymore? Is it denied anymore? It doesn't make sense. It may seem easy where you can just go through the other data points and say, oh, well, obviously all the things below that new line now have to be set to denied instead. But it's not always that simple. A lot of the problems you face, a lot of them were legislative. Some of them had much more complicated solutions to that. The only way you can modify that old data would be to have a professional go through every single case, millions of them, and reassess whether they'd be good or approved or denied based on the new standards. And that is not only expensive and really difficult, but potentially impossible. Another way you can do it is with your new data that you get from doing more claims that people do by hand. You can weight the new data as more important than the old data. You could say, OK, I want you to take this old stuff a little bit into account, but the new stuff really into account. But there wasn't really new data because they haven't done anything with the new claim system yet. As a result, he ended up having to scrap the product entirely. And this is actually a common problem. Anything that involves law or changing benchmarks has a possibility to invalidate your data. If you have a big data set expanding over a long period of time, also look at what factors affected those results of that data before you go into actually making your product as well. If there was a change in benchmark like 20 years ago and you have 50 years worth of data, anything beyond that 20 years might not be valid for you anymore. So my last example I'm going to give here is one that you guys might have heard about because it's been in the news a bit recently. Basically, Amazon made a hiring AI that turned out to be pretty biased towards women. And sure, it was biased, but it wasn't intentional. These are very smart people with a lot of money, a lot of talent, who really did their best to try to remove bias from the system. So what happened here is most of the previous applicants were men. Most of the previous hires were men. And as a result, and only a few of them were women. And as a result, what do we get here? We saw this earlier. We have a majority and a minority class. So what they tried to do is they tried to remove the importance of gender from their roles. They removed things like gender, name, age, and a bunch of other factors from the resumes to try to make them more even. And it sounds like that would be a good solution, but unfortunately, that didn't work. So why didn't it work? Well, all right. There's a difference in how men and women tend to write and tend to speak. Men tend to use words like captured, executed. They're captain of a men's team. They use language that's very solo. They use I a lot. And they tend to use very competitive language. Women, on the other hand, tend to use words like organized, volunteered, or assisted. Things like woman's team captain, the word woman's never going to appear on a men's resume. So of course, the example data or the training data wouldn't have that in there and would discredit it. And they also tend to use team or family-based language. You'll see them using we and us more in those resumes. So even without intending it, they ended up having a bias that they didn't expect. This happens in other places in the world as well. Take the Conservatory of Music in San Francisco. What they tried to do, they noticed that there was an issue where they hired a lot more men than women. And they tried to make blind auditions for music. So they'd go behind a curtain, they'd play and leave. But there's still a lot more male hires than women. So what they did is they put down a carpet because they found out that the reason why they were biased is that they could hear the woman's heels clicking on the floor when they walked in. And after they put down the carpet, the hiring ratio became around 50-50. Bias can exist in places you don't expect it, and it matters in your code, especially when you're learning. There's also a funny joke I read on the internet this morning, which said, oh, well, the robot apocalypse didn't really go the way I expected it. You think they'd be using lasers and guns. And the man responds, well, they used historic training data, and most of the historic data and most of the historic wars were won with swords. And that's the reality of machine learning. You're learning from old data. You're not learning new things. So there's a lot of ways you can get data. For example, if you want to work with preprocessed data sets, and you want to maximize your work on your algorithms and get better at your tools, I'd highly recommend just Googling available machine learning data sets, and you'll probably find something that you can work at that's processed and ready to go for you. There's also a bunch of places you can get data without having to process it yourself, or with minimal processing, or places you can scrape data from if you don't have access to your company's millions of records of claims data. So for example, Reddit has a great API to be able to pull information from that. Twitter has a great API, and I'm going to go into an example about a Twitter API after, and a lot of others. So we're going to go into my favorite slide here, and it's going to be a little bit of a story about, this one's a personal one of a project that I did right when Donald Trump became president. So one thing you might remember from Donald Trump becoming president is that the stock market, every time he tweeted anything, went off the rails. And as a result, I tried to predict the stock market with Trump tweets. You might have heard an open source project that was like this. That was not mine. It was released like 2 weeks later, and I'm still salty about it. And mine works a little bit differently. So what I'm trying to do is I pulled in data from Twitter, from Trump tweets. And I use Google Cloud API to do natural language processing on it to figure out two things. So let's take a tweet that he actually said, our southern border is insecure. I cut off the rest of that tweet because on top of being inappropriate, it also doesn't contain the content that we care about. So first of all, we're going to figure out the context of this piece. What are we talking about? Well, our southern border, he means Mexico. And then we're going to figure out the sentiment. Is this a good or bad thing he's saying? Well, insecure is a negative sentiment. He's saying something bad about Mexico. Go figure. So from there, I did a bunch of data scraping and comparisons and word2vec to figure out a bunch of words that associate to Fortune 500 companies. And I'd say, OK, Mexico associates to the Fortune 500 company América Móvil. And, well, it's a negative sentiment, so we should short those stocks. Put those together, and you find something called the plunge. It doesn't really equal, but I wanted to put the equal sign in there. This is actually an example of Boeing, after a Trump tweet, plummeted their stocks temporarily. So it's a real thing that happened. People freak out, the stocks drop, and then go back to normal a little bit later. My algorithm was faster than the stock markets could react, so I'd short the stocks and buy them back shortly after with a pretty high degree of success, actually. There's a lot of difficulties associated with projects like this, though. For example, I don't know if you've read a Trump tweet. It's not always the best English that you're reading, and being able to process that can be a little bit difficult and doesn't always get the kind of results you want. Also, adding your own sentiment. For example, my algorithm considered Ivanka a negative word and would treat anything with Ivanka in it as a bad thing. Cool. So that's a little bit about data and some things to keep in mind while you work on it. Now we're going to look at what comes after data. So second thing I want you to take away, most problems are not machine learning problems. It's my disclaimer I give at every single one of these presentations I do. So what is a machine learning problem? Well, a machine learning problem has big data, millions of data points. It's complex, too difficult to solve by hand. It's non-deterministic. That means the same input to a system doesn't guarantee the same output. For example, human interaction. If I go up to someone in this audience and I high-five them, they're probably going to high-five me back. If I keep high-fiving them 10 times in a row, they're probably going to get a little weirded out and react differently, unless they're a sim, in which then we get married. It's also many-dimensional, so there's a lot of factors that influence what my ultimate result will be. There's a lot of tools to help you when you have your problem defined and you've determined it's a machine learning problem. Maybe it's classification, regression, whatever the problem is that you can use. I personally tend to teach and use TensorFlow, but I've heard great things about PyTorch and Keras and many other tools as well. I'd highly recommend using tools. So let's remember what this slide is. Cool, that's really helpful. Oh, right, training and testing. Okay, so once you have your data and you have your model together, I'm not going to explain that part because that's very much the tutorial and what it teaches you. Now you have to train your data. The tutorial usually says, okay, take 70% of your data to train, 30% to test, and you're good. That's not actually the most efficient way to do this. It's a very common method that people call k-folds cross-validation. And it sounds complicated, but I'm going to explain it to you in a little bit of an easy way. So we have a data set here. And let's say we take 1/3 of that, and we say this is our testing data. The rest is our training data, all right? That's going to be our first fold. So we train our model with that training data and test it with that testing data. Then we refine it and do it again. This time, we take the next third as training data and the rest, or test data, and the rest of it is training data. That's our second fold. We do it again, in this case 3 times, until every single piece of data has been used as training or test at some point. In this case, our K is 3, because we do it 3 times for 3 folds. Now, a little bit of a disclaimer about doing this. The most effective way to do this, and the most accurate, I guess is what I should really say, is n-1. Or you use every piece of data as training data once by itself. So you end up doing the training, or you end up having as many folds as you have data -1. And this takes a really long time. So for example, that's me in university. And there is a university computer with that school I went to. And I did a little paper in a machine learning class where I trained a bunch of data on my whatever laptop I had. I had 250 million data points to work with. It took me 54 hours to train my model doing 70 train, 30 test. Only 1 training set. So if I wanted to do this for every single piece of data, if I wanted to do n-1 k-folds cross-validation so I could get my algorithm as perfectly accurate as possible, it would take me about 3.5 million hours, or about 1,500 years. Didn't really work out for my paper, but so that's a good thing to keep in mind when you're dealing with more advanced test methods. The more times you have to train, the longer you're going to have to spend. It's a good idea if you want to compare different kinds of models to solve your problem to take subsets of your data and train with that instead, just to get a feel for what the best model is before you throw all your data into it. All right, so one of my friends told me recently about this awesome thing called Google Collaboratory. It's basically a free Jupyter notebook that has available TPU, GPU, and it's completely free that Google has. I'd highly recommend looking into it if you don't have the processing power yourself to do machine learning. It's a great tool. I only found out about it recently and have been using it since. Highly recommend for anyone who doesn't have their own big servers to work with. All right, machine learning and mobile. This is AndroidTO, so built-in machine learning, sort of. There are solutions for iOS, but we're going to really look at Android and MLKit for this one. So MLKit offers a couple out-of-the-box things: image labeling, barcode scanning, face detection, landmark detection, and text recognition. You can also upload your own small custom models using TensorFlow Lite in order to be able to use this service. So typically, if you want to use machine learning on mobile without using something like MLKit, you have your app contacts your server gets your models, and then goes backwards until your app has the data that it needs. MLKit's easier because you don't have to run your own server or create your own models. You can just use these things out of the box. Now, the models are not actually on your phone. It's still contacting a server and getting the data from there. If you want to upload your own code, instead of having to run your own server, you can upload your models to MLKit using TensorFlow Lite and be able to access it directly from your app without having to host your own servers. So we're ready for the real world. Some priorities and good to know. Hardware is a bottleneck. So from your phone can't house the machine learning itself. But I have a pretty extreme example of that. China. China has this awesome thing for their police. They have facial recognition glasses. These glasses can process somebody's features, send them to a server, and get them back, and then display it visibly so they know who they're looking at. Now, this has a problem, though. Even if the server was as fast as humanly possible and could instantly return, there's only so much hardware you can put in glasses. These glasses need to process features, send them, get a response, and then show what is on the, and show what they're seeing on the glasses, which is really complicated. As a result, they have to usually look at a person for 20 seconds straight still in order to get a result, which isn't very effective, except they did catch a cocaine smuggler at a train station once. My third thing and final thing I want you to take away: you can be held accountable for the shortcomings of your software. This is one that's particularly important to me because this one, if you're not Canadian, is an iron ring. It means that I at least got an engineering degree in Canada, and I care a lot about ethics, and that's something that's really important to know. So for Amazon, for example, with their hiring AI, is accountable for potentially not giving opportunities to women who might need it. And this can have some pretty serious implications, especially when you start considering medical imaging as well. If you want to jump straight into medical imaging and you give a false negative and you're saying, there's no cancer there, you don't need to look at it, and there was cancer there, that's pretty bad. You probably don't want that. So if you're doing anything involving that might have ethical implications, make sure you keep that in mind. So last thing, expect the unexpected. You guys might have heard about the Microsoft TE algorithm that happened. So Microsoft tried to make an AI chatbot on Twitter. Now, I don't know if you know that people are people, but people are people. And user input ended up causing TE to say some rather inflammatory statements. It took me about an hour to find one of her tweets that was wrong but not horrendously offensive in order for this presentation. And this is the kind of problem when you don't sanitize your inputs and you don't pay attention to your data. So, a little bit of recap. Your algorithm is only as good as your data. Most problems are not machine learning problems. Keep it in mind. You're responsible for the shortcomings of your software. Machine learning can be slow, and machine learning can be unpredictable. It is trying to be the human brain, and I don't know if you've ever gone into your kitchen and opened the fridge and forgot what you were getting, but we have flaws, and so does your algorithm. They also don't have as much of an understanding as we do. For example, if you feed an algorithm only black and white pictures, it's not going to be able to tell what the color green is. We as people have a much wider understanding of the world. So where do you go from here? Some next steps. Perfect your algorithms with pre-processed data sets. Take that MNIST and do it the best until you understand how to use the tools really well. All you Android users, fret not. You want to work on a real project. I'm sure all of you have analytics. Analytics are great. You can figure out what to do with user data. You can personalize people's experiences. You can recommend products. There's a lot of opportunities for what you can do with analytics. Consider existing tools. I like TensorFlow. Don't reinvent the wheel. Most of the science behind this is from PhD mathematics students. It is very hard to invent your own machine learning, so use what already exists. Online courses exist to help. One of my friends did one recently in Coursera, which was really great. Google is your friend, as in with all development. And try it yourself. Go out there and actually try it. So I do have a question slide, but I'm pretty sure I have like 20 seconds left. So if you want to grab me at the after party or something like that to ask me some questions, feel free. I do love talking. So thank you so much. I'm Kyri. And have a great AndroidTO.